Welcome to our math booster about integration. Oh, what is integration? In this video, we're going to get a crash course about what is integration, what are the rules for integration, and how do you apply it to kinematics equations and things like that. And of course, as a last add-on, how to deal with special kinds of equations when you see them. Okay, so first things first, what is integration? It is, well, in English it means like put together. But in maths and physics, here's what it means. Now let's say you have this graph here. I'm going to call it just a normal graph lah. Okay, so y-x. And then you have a curve or a straight line or something like that. Let's go with a straight line just to start off easy. So maybe it looks something like this. Okay, so one task, if I ask you, is how do you find the area under the curve? So from 0 to some point here, this shaded area. Now we have done this before, right? In physics, for example, if we say, oh, if this is Hooke's law, F equals to kx, then I need to change my axis a bit. So this is force against extension of a spring. I want to find the area because the area is the elastic potential energy stored. Elastic potential energy like that lah. How do you find the area? You can say, oh, miss, easy. You just take the triangle area. Yes, we know triangle area is half base times height. But where does this half base times height come from? Actually, its fundamental lies in integration. So I'm going to show you another way you can do this without using the half base times height formula right away. So there's this fancy thing called integration where it's like this. If I say I have a function or something x, let's say x, and I want to integrate it, which means if I have a graph y equals to x, I integrate it to find the area. So the area is integrate area under that curve, right? So integrate x with respect to what? X is my only variable here, so dx. Okay, how do you do this then? You kind of have to do the reverse of differentiation. So what you have to do, first step is, what is the unknown? Oh, x. So you write there, x power is 1. So you do add 1 power and divide by this new total power. So this is 1 plus 1 more. Okay, and you're done, pretty much. I mean, this is the basics of it lah. Okay, so if you're integrating from, let's say, an area of 0 to 1, that means if you have a graph like this, y equals to x, you're going from 0 to 1. What is this area? That is what we're looking for. Okay, so if you simplify the math a little bit, this will be 1 over 2 x square. And there, you've got your area under the curve, which is just half x squared for a straight line graph like this. Okay, so how do we apply it to this one then? So let's say I want to find the area under this force extension curve. You do the same thing. So force equals to kx. K here is some constant lah, so we don't care too much about it. It's just a constant, spring constant. But if I want to find the area so under the curve, from, let's say, you stretch a spring from 0 to, what do I call this? Some extension x. Let's put it green color, extension x. Then I will need to say, oh, I want to find the area under this straight line, kx, y equals mx plus c. So I need to integrate kx with respect to, what's your x-axis? X here, right? So you write here, x dx. And you're integrating from 0 to green x. That's what we call the limits. So from 0, the area, all the way until where you want to find the area. So green x lah. Let's just call it big X. Okay, so let's do that. But before we go on, do you know what's the area under the curve? I already said it, elastic potential energy. So we can just say, elastic potential energy equals to, what is the answer for this? Now the constant is not affected. K is not affected, so you can write K first. What is affected though is the X. So how do we do this again? Now remember X, the power originally is 1 ma. So plus 1, it becomes 2. divide by the new power. So I need to label this so you can remember. This is the new power. This is the old power of the unknown plus 1. Okay. And since we're going from 0 to x, let's write the limits here outside the bracket. This is just a way of writing it. So how you go on from here is, now we need to substitute in your values. So let's put a bracket. The first one, you plug in your green x here. So if I plug in my green x into the formula, it will be x squared over 2. Minus, what's the other one? 0. So you write there, you plug in 0. Let's call this a purple 0. 0 square over 2. Okay, so I use my limits, I plug it in and I calculate. So in the end, what do we get? 0 over 2, 0. This whole thing is just 0 already, gone. So all you have is half kx squared. Hang on a second, have we seen this before? Half kx squared is what? Half kx squared is the area under the graph. So this area is, well, it can be calculated by half k, well, the x is a green x, x squared. You see, magic, you found the area, which is also the area, the triangle area, half times base times height, things like that. Very interesting. So area of the triangle, if you want to use that method, area of triangle would be half fx, which can also become half kx squared. So you see how it comes together? So the purpose of integration is we find areas. Whenever there's area, we can use integration. Now, how do we apply this to kinematics though? Let's come down here and start a new trend. So the question is, how do we apply this to kinematics? Now you need to review a little bit. Remember how we defined displacement, acceleration, and velocity before this? In the previous math booster, we talked about differentiation. So we were saying like, oh, if you have a displacement function or curve or equation, whatever it is, s equals to ut plus half at squared, for example, and then you maybe plot a graph of that thing. So maybe look like this lah. Something like this. Pew. I just give an example. Then if you want to get the velocity equation, velocity is defined as the rate of change of displacement. And we know the equation is v equals u plus at, but you can do differentiation. You differentiate the s equation, okay, differentiate with respect to time, then you get your v equation. Okay, and it's a gradient, no? So the gradient of the st graph will be your v graph. So vt. So dy dx is basically finding the gradient. So vt graph maybe look something like, I don't know, plot a graph lah, okay? And then you come to a next step. Acceleration we define as a rate of change of velocity. So it's one step further. You differentiate v equals u plus at. Okay, differentiate again with respect to time. You should get acceleration equals to just a only. Okay lah. Let's call this gt. A equals to negative g. Okay, let's put like that. EU minus gt is copied from the before one, so your graph look like this. So your acceleration graph is going to look like this. Okay, that's how they relate. Velocity is the gradient of displacement. Acceleration is the gradient of velocity. Gradient. And how we do the gradient is we differentiate. But it just so happens that integration is the reverse of differentiation. Wow, what does that mean? Integration is a reverse differentiation means if I have a velocity equation and I say, I forgot the displacement equation, how to find? You can actually integrate. And integrate will undo your differentiation. So you integrate your velocity with respect to time. I just write the symbol, okay? This curly symbol means integrate. So if you integrate velocity, you will get displacement. Why is that true? Because remember when we say, what is the area under the velocity time graph? Here, the area, like we talked about earlier, is actually the displacement. How far has that particle or object traveled? And we talked about area as integration. Okay, a way to find the area is by this thing called integration. So yeah, we integrate velocity, we get displacement. I'll show you a demo how you can do that. And the same thing, if you integrate acceleration, area under the acceleration curve, we hardly do this lah. You integrate, you will get velocity. So this is how everything relates. Rate of change, gradients. This is rate of change. And integration is all about area under the graph, which is very useful. So I'll give you a demo. How would you integrate v equals u minus gt and get this s equals to ut minus half at squared? So let's say you have v equals to u plus at. But in this case, since we define downwards as negative g, so we have v equals to u minus gt. Okay, we start off with this. Now the question is how to get displacement equation. Here's where we have to integrate. But how do you integrate? You just put integral sign there. Here's how you want to do this, step by step. Velocity, we say, is the rate of change of what? Displacement. So we say velocity is ds dt, rate of change of displacement. So rate means there's a time there lah. Okay, equals to u minus gt. Now what? Now we're going to do this trick called rearranging the things. So what you can do is the ds you leave here. The dt you move to the other side. See what happened? Then we integrate both sides. So we add this snaky shape there. Okay, now we're ready to integrate. So what's happening is, what are we integrating on the left side? Oh, actually there's nothing here, means it's just 1 with respect to ds. ds just means I'm integrating with respect to s. On the right side, you are going to integrate this whole thing. U is a constant, g is a constant. You're integrating t. Oh, t is the one that will be affected because we're integrating with respect to t. Here on the left side, no s. What's going to happen? We'll see. Okay. So how to do this? Let's do it slowly. On the left side, if you integrate a constant, what is the power of the unknown? Basically, you can say there's s power 0 there lah. Anything power 0 is 1 ma. So if s power 0, the new power will be 0 plus 1. So 1. Divide by 1. Okay lor, 1, 1, 1, 1, 1 everywhere. Equals to, on the right side, we have to integrate u. U is a constant, so there's t power 0 inside here. So we need to increase the power of t. So t will be power of 1. Oh no, divide by 1. Okay lah, I write everything for you. Okay, the next one will be gt. gt, oh, t already got power 1. So you increase some more, become power 2. So gt square, but must divide by the new power. Now there's one thing I didn't tell you, but I should tell you now, is that you can actually add a constant. Don't worry about the constant too much. Just FYI, there's some random constant there lah. So for now, we'll just ignore the constant, but just know that there could be a constant there. Anyway, so let's continue. So simplify a bit. S equals to ut minus half gt squared. Wow, do you recognize this? This is our displacement equation. Well, the original form is sut plus half at squared. So do you see what happened there? When you integrated, or when you use integration on this velocity equation, you get your displacement equation. And that is exactly what we're talking about here. Okay, velocity, you find the area under the curve, you're doing integration, so you will get your displacement on the left side. To double check, if you want to be sure, then you double check. Check. You try to differentiate the equation down here. So ds dt will be d with respect to t. You direct the whole thing inside there, half gt squared. Do you remember how to differentiate? Okay, so let's double check. What do we get? ds dt is v, velocity, rate of change of displacement. So here how? T is power 1. So when you minus the power already, it becomes 0. So it's just u minus half g. What is this? When you differentiate t square, t power 1, but then the 2 comes in front. So what you have is v equals to u minus gt. Is this correct? Double check. Yes, it is correct. So you're going back and forth. So to summarize, displacement, you differentiate, you get this. You integrate, you go back to displacement. And you go back and forth, back and forth, back and forth, back and forth. It's like integration is happen to undo the differentiation for you. So you can use it as an undoing tool to go between velocity and displacement equations. For any velocity displacement equations. For example, your favorite one, okay, this one, remember this? Sine and cos, sine and cos, sine and cos. You differentiate sine, you get cos. You differentiate cos, you can reverse this whole thing, you know. So if you want to upgrade this picture, let's add some integration. So it means if you integrate cos t with respect to t, you should get what? Sine t. Because you reverse mark. This is the basic idea lah, okay? So when you integrate cos, you get sine. So everything is reversed. You integrate negative sine. This is not s, this is integral. You get cos. So see how the arrows are reversing? It's just reversing. I just draw an arrow, everything lah. Reverse, reverse, reverse. Rub off this, rub off that. And there we go. So yeah, this is a very useful tool whenever you come to any kind of equation that is thrown at you. Especially when it's kinematics, got velocity, they got displacement, they ask you to find the different one. You just need to know this relationship. Displacement, you differentiate it, you're finding the rate of change, which is a gradient, which is velocity. Okay, if you want to find displacement from velocity, you integrate, you're basically finding the area under the curve, then you get displacement. Okay, so the last part of this video is just to get you to practice a little bit with some weird equation that you've never seen before. So let's say I give you an equation, I throw you an equation, what v equals to, what shall I come up with? Let's do this one, 2t squared minus t. Aha. And I say, okay, this is the velocity graph of how a particle is moving back and forth. How are you going to find the displacement equation? Question mark, question mark, question mark. How to find integration. So you might remember, you're finding area under velocity time graph, which means you're basically finding displacement. So what you need to do is, remember that velocity is rate of change of displacement. So you can say velocity is ds dt. Confusion here, ds dt. So you write here ds dt. Next step, we want to integrate. So let's rearrange ds on one, all the s on one side. Then you put all the t on the other side. dt. Treat this like a fraction lah. Okay, numerator and the denominator. Okay, now we're ready to go. We integrate whatever is here. I guess it's only 1 times ds lah. Then you integrate both sides. So here also must integrate. So what you get? Integrate 1, you should get s. If I'm going too fast, just pause the video. You try it out yourself. Then you come and check if you got it correct or not lah. Okay, and this one, how to do? 2t, the power increase already, so become 3. Divide by the new power, okay, minus t. Wow, this one the power is 1, right? So become 2, divide by the new power. So this would be your new equation for displacement, 2 over 3t cubed minus half t squared. So to end the video, I'm going to do a challenge question for you to see. This one, the scenario is a bit unique. We need some tricks to help us out here. But let's say I give you an acceleration curve. Acceleration equals to, I could say 3t, but let's make it a little bit tricky. What if I say the acceleration is 2s? What is s? This s is displacement. So acceleration is changing depending on displacement. So you'll be very tempted to say, okay, if I want you to find what's the velocity curve. How we do this? You think of, maybe acceleration is rate of change of velocity equals to 2s. But then you come to a problem. You're like, hang on. Here, if I do dv equals to 2s dt, and then I integrate both sides, I will have a problem because this is s, but with respect to t. So how? Gonna have a problem here. So we can't do that because previously, whenever you integrate an equation here, all the t is here, integrate with respect to t, also t. But here you got a problem, here got s, here got t. So we can't use this anymore. We need a trick to help us out. And that trick is called the chain rule. The goal of this chain rule is to get dv ds into the equation, because then only we can integrate. We move the s to the other side. Okay, so how to do this? Well, first step 1, we see what do we have here. We have dv dt, so we write that down. Okay, and I want to get rid of the time. I want everything in terms of displacement, so I can treat this like fractions, right? So I can say, I want to get rid of t, so I put my dt here. But I want to introduce s into the integral equation, so I put ds over here. Okay, can this work? Maybe. So if I do this one multiply this one, what should I get? If you treat it like fractions, you should get dv ds lah. 3 over 2 times 4 over... Actually, that's not a good example. Sorry, wrong example. Throw back fractions. If you have a over b times b over c, what do you get? B cancel out a over c. So you are treating it like fractions. So this one is true, right? You want to get rid of time, so time will cancel out. So how can you plug this inside your equation on the left? Plug in dv lor. So we rearrange a bit. dv dt equals to dv ds. Move the fraction to the other side. It will become ds dt. Okay, so now we can use that. So we plug in here a chain rule. We just created it based on fraction. So dv dt will be dv ds times ds dt. Very nice. I like this. We'll see why it will help in a bit. So now ds divided by ds actually is gone. So very good. We have dv dt over here. Ding. Sorry, I just realized the error. My brain dv dt plug in is I copied the wrong equation. dv ds times ds dt. No wonder I wonder something's funny. dv ds dt, correct. Okay. So now what? How would you do this? Don't panic. Just remember that dv ds times, we know this thing. What is the rate of change of displacement? Velocity. So let's put velocity lah. Okay, so that makes our life a little simpler. Now we have everything in v, everything in s, t is gone. Very good. So now I just rearrange a bit lah. So v dv equals to 2s. My ds moved to the other side already. Multiply both sides by ds. And of course, I integrate. Now this is like normal. So integrate v dv, you get v squared over 2 equals to, here 2s, here original power 1 become power 2, divide by the new power. Okay, then plus c lah. Constant lah, some constant. But actually you don't want to write, also can one. I just put that. So this is your new equation. So your equation will be v squared, what Then 2 and 2 cancel out. V squared equals to 2s squared. If you want to simplify a bit, v equals to square root 2s squared. Or square root 2s. There. So this is a challenge question lah. What happens if your equation is in terms of displacement instead of time? Because usually time when it's in terms of time, it's very convenient because all our kinematics is rate of change. Rate of change means time is involved. But if you have something else like this, expression depend on displacement. Why got displacement? Then you have to do what we call the chain rule to get rid of time. So we get something like this one. A substitution to get rid of time. Okay, so this is all the crash course about integration. No worries. If you have any questions, please feel free to ask so that you know, like, oh, okay, I think I kind of know what's going on. That is all for integration. See you in the next Math Booster.